Hello, welcome learners of physics. So we are now very deep into AC. You have hopefully watched the first video about half-wave rectification. Half-wave rectification is when we only use half of the wave. So if you look at this drawing, you will see that only half of this AC on this side is output here. All right. So this is half wave because we only use the green half. Like for example, this wave is not captured because the diode is blocked. Here, when it's green, it is fully used, not used, fully used, not used, fully used. So we only use half of that wave, and then you might be thinking to yourself, this is such a waste. There's this half wave here that is flat. Although technically you could connect a capacitor here to smoothen it, it makes us think, is there a way for us to connect a circuit such that you will get the whole goodness of the alternating current? All of it, not half of it, but full wave rectification. All right, so that would be what this video is about. What is full wave rectification? How to connect a circuit that creates full wave rectification, where to put the capacitor, and how to draw this output graph. All right, so if you're ready, let's go. Okay, here we are back in our notes. So I'm going to now, in this part of the lecture or the video, draw out a possible circuit diagram for full wave rectification. But please bear in mind that there are several possible diagrams. It's a bridge circuit. How would you know which one is the correct or more suitable one? Well, I guess there are no more suitable ones. There are just different ones. And your skill set here is to know how to draw a basic one and also know how to analyze the bridge circuit. So if you are actually a creative thinker, you might actually have in your head how the diodes should fit together. But let me first draw a basic circuit first. So on one side, what you will get is alternating current that you are trying to rectify. So I'm just going to draw a terminal here. Draw the waveform. Okay, this is your AC supply. So to find this AC supply, this one is your input. Okay, so this really standard alternating current, AC supply, and I'll label here, this is my V in. Okay, and right now I am going to have to connect it to 4 diodes such that we have alternating current. Direct current, changing this to direct current. So the first thing that you should know about the circuit is that they are normally drawn in a diamond shape. Okay, so let me first draw a diamond shape first, or try to draw a diamond shape. All right, something like this. Okay, I'll connect it to the supply later. And the second thing that you should know about this diamond shape is that we will place on each side a diode. All right, so who thought of arranging like this? There'll be some smart person somewhere. If you thought about this, good job. So these two diodes will be connected with the opposite end. This end and this end will be forward biased in the same direction. Okay, so maybe this one would be pointing, let's say, like this. Okay, so just a reminder about the diode. Whenever the arrow is drawn, okay, let me draw it bigger so you can see. Ding, 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 ding. So we draw the diode this way. Okay, I shall zoom in. So whenever we draw a diode like this, right, if the current flow this way, this is what we call forward bias. So current can flow. All right, as you probably already understood this from the first video. Okay, if you connect it like this, but the current flow in the opposite direction, I guess to follow the simulation I've given you just now, I should probably change this to green. Okay, so forward bias is when the current can flow. Okay, so, and reverse bias is when the current cannot flow. So let's write this down. Forward bias. Reverse bias is when the current reach here and then it goes knock against the wall, the vertical line. So this is reverse bias. Reverse bias is non-conducting. Current cannot flow. So no more. Here there's no current. Alright, so we're going to draw the biases of these two diodes to be identical. Okay, they're going to be pointing in the same direction. Alright, and the opposite one will also be pointing like this. Miss, do they need to be pointing up? Can they both be pointing down? Oh, this one, why don't you go and figure it out? I can't tell you all my secrets now, can I? Okay, so the whole idea is you will have two opposite vertices, all right? And then they will be pointing in the same direction. So this blue and blue is pointing down, the green and green is pointing that side. That side? No, sorry. My camera is flipped. Pointing this side, okay? So this one is pointing up, up. This one is pointing down, down. Okay? Or like what I tell my student, you go up the mountain, you come down the mountain, you come down the mountain, you go up the mountain. There are many ways to rotate this. Since I'm using one node, this is how you can rotate the circuit. So this thing, okay, let's see if I can rotate this by grouping this. Whoops. Oh no, what is happening to my one node? Whoops. Okay, I'm back. I have grouped this one. So I can rotate this several ways. Okay, so I can rotate, let's say I rotate to the left. So this is a possible circuit connection. Okay, notice that the blue ones are still parallel, the green ones are still parallel. Of course, I can keep rotating this, right? I think you get the idea. There's no even such thing that says that, oh, we must rotate it counterclockwise, 90 degree, counterclockwise. It doesn't matter. So no matter how it's being rotated, the circuit has to have two sides parallel pointing in the same direction, two sides parallel pointing in this direction. So you can tell this whole thing can be rotated many different directions. You know what? Since I rotate already, I'm going to keep it this way, okay? So two things parallel, two diodes parallel, and this orientation can be rotated. If you're not happy with the rotation, what can you do? You rotate your exam paper, okay? Okay, so I'm happy with this. And one thing you have to be careful about connecting this to the supply is that the supply generally will take opposite vertex. So this supply here is going to connect, let's say I connect this to the top vertex, all right? So I will connect this to here, bloop, and I'll connect this to here, bloop. So I'm going to draw a dot here. Okay, so at this point in time when you study electricity or electronics, the dot here means there's connection. If there's no dot means there's no connection. Okay, and you see the opposite vertex is so lonely. Here and here. So this side, I'm going to connect this. But whenever I draw this way, it means that the purple wire is on top of the black wire. They don't connect. It's not a T-junction, it's a flyover. It flies, the purple color is either above or below the black wire. It's not a T-junction, okay? If it's a T-junction, we will draw a dot like this. Since there's no dot, it's not a T-junction, all right? So on the opposite vertex, we need to draw the output, okay? So normally, right, to measure this output, we will put a resistor, very much like the full wave rectification. Sorry, the half wave rectification, we're going to put a resistor here, and this resistor is R. All right, so what do we do to measure? It's normally here to here, we will connect to our good friend, the CRO, to cathode ray oscilloscope. In fact, this AC supply normally is also a signal generator. Okay, so this is to prepare you in case you need to write a paper file. Okay, you can put a signal generator. This part is connected to the CRO, or I guess if you want to, you can connect this to a voltmeter. All right, so let's start by thinking about what is the pathway of the current. Okay, so we're going to have to be a bit strategic about this. Let's say I start with one of the top cycle being here is positive. So let me try to write down. This is positive. Okay, so this is for this one. Okay, and I will treat this as this cycle. This is the positive cycle. Okay, current will flow in one direction. Of course, the magnitude is not the same. If you watch the simulation just now, the charges will flow faster than slower. Later we watch it again, okay? I can't pull it here without killing the computer. So when this is flowing, the current will now flow like this, like this. So the current will come out from here, okay, flow this way. Where to go? Should this current go to the blue diode or should it go to the green diode? What do you think? And then this is where you know what you are drawing is wrong. Because when I say you can rotate in any direction, this is a direction where the current is stuck. So stuck, then how, miss? Well, you need to flip somebody. Choose one side to flip. Okay, so this is how you can also amend your circuit. So where are you going to flip? Choose either one. Let's say I choose the blue one. Okay, so I'm going to flip the direction of this blue diode. Okay, normally when people do this, they give you the perfect thing. No, I show you a work in progress. Or I give you an example of how you don't have to panic. You can always flip. All right, so like this. So although it can be rotated, not every orientation is okay. So you connect this way down. So now the current is okay. I know where to go because just now both diode is blocking. Now this diode will connect. Yay. And you can see this green diode is blocking. Okay. So this one will connect this way. The whole idea is one have to be up, one have to be down, in case you're wondering. So the current will flow from here to here. All right, so I'm just going to continue the arrow, okay? Current flow like this, like this, like this, like this, like this. Yay! And it will go back up this wire. Where should this current go now? So you have to understand now, the purpose of the current is to return to the negative terminal. All right, so the negative terminal at this half cycle is here. The current is like, 我要回家, I want to go home. Okay, saya mau balik rumah. So to go back home, if you go up this green one, it's such a, this does not bring me home. In fact, it brings me to where I first started. That's not what we want. So we will go back down so that we can go back home. Okay, so this means the current will flow down this way. And of course, it's not going to go up because current will flow from high potential to low potential. So here, the potential here is higher. Okay, so if let's say you don't want to think about my narrative, you could think about the potential difference. Here is high potential, higher than this point. So then the current will flow down here because here is low potential. All right, current flows like water from high to low potential. Okay, so we're gonna okay, we're home now. All right, the circuit is complete. Let me draw a few arrows to show this. So the current will flow this way and return. So this first half cycle, indeed, for our output to our CRO. So here to here is to measure V out. So I'm just going to label this one as my V out. Okay, so when measuring V out, we definitely will get the actual half cycle here. So let me try my best. So this one, you will have your wave. No problem, sir. But the $100 million question is, what about the negative side, Che? This negative side, are we going to get also current flowing in the same direction? Or will it be caught somewhere and cannot flow? Well, I'm happy you asked because we are ready to go through the process all over again. Let's say this is the negative cycle. So for negative cycle, I think I will use green. Okay, so this is your negative cycle. For negative cycle, right, this one will be negative and this one here will be positive, meaning the current will reverse flow. Okay, so to make this a bit easier, I will redraw the circuit, okay, and the side, and then we will plot the second half cycle. All right, I'm back, and now we are ready for the second half cycle. So the first cycle one, I have left it here, right? The current will flow in the direction of the blue arrow, so it will trace this way. So now we're going to swap the terminal such that this bottom one is positive and this top one is negative, okay? So I'm going to just gently, slowly nudge this away. All right. And we are ready for the next one here. Brand new and fresh. And just in case you want to double check, it's the same circuit. Okay, I didn't change anything. The diodes are still pointing downwards for the blue one. The green one is pointing upwards. Okay, so let's go, kids. So negative is the blue cycle. I will use a blue highlighter. So we will swap just now from this top part as positive to the bottom part as positive for the next cycle, because AC is swapping, right? So now we're gonna try, go this way. Okay, so the current will come out from here, and then pass through here. Ooh, spicy. It reaches this junction. Where should it go? The blue diode is reverse bias. Current cannot pass. So it has to flow through the green diode like that. Okay, and then you will notice that it cannot go to the blue diode. Blue diode still reverse bias. So the only way it can go is down. Hiya. So the current will go down, pass through the resistor, same old resistor, okay, and then go up. So let me label the direction of the arrow first. Okay, your current will pass through this green diode, forward bias. Since it cannot go up to the blue diode, the only way to go is down, traveling this way and coming here. So now when it reaches this junction here, this junction now has two choices. It can either go down, which we will encounter the same problem, because here is a higher potential. Where the current came from will always have a high potential, because like water flow, current will flow from high potential to low potential. So the potential here is the highest, the potential here is higher than here, and here is higher than here, and here is higher than here, and here is higher than here. Okay, so if that is the case, the current definitely cannot go down to the blue one because the potential here is high. Here there is a high potential, and here is the low potential. So we will flow from the highest potential. I guess I will say this is higher potential, and here is high potential. Everything is relative, right? Okay, so it will flow to the blue one. To the green one. So a good way to remember is that always is the opposite one that conducts. Okay, especially when it's drawn in the bridge like this. So now the current will flow up this diode. Okay, don't forget its whole purpose is to return to this negative terminal. So then the current will continue to flow and reach back to the negative terminal. All right, current will go this way, like this. Yay, the circuit is complete. And let's check the output. Both yellow and blue cycle have output pointing in the same direction. Oh, yes, it does. Because if you look at this resistor here, this one, this is the positive terminal. Let me change color a bit. This is the positive where the current go in, and this is the negative where the current go out. So the current is flowing through the same direction, positive here when the current go in, negative when the current go out, for both cycles. Okay, let me zoom out a bit so you can compare. For both cycles, the current will flow in the same direction through the resistor. Wow, so in this case, it means that the current flowing through resistor R is always the same direction. Okay, so in this case, this means that this blue cycle here, okay, which I will then now use a green pen, I guess I'm going to extrapolate downwards, will also have a loop like this. So congratulations, my friends. We have not wasted any of our AC. This is a better efficiency, and your parents will not hit you for wasting current. Okay? Don't waste current. We're going to use this. All right. So if that is the case, right, then whenever we flip back to the positive cycle, we are going to get the same pattern. Okay? Which is like this. All right, and then this one until here would be like this. You try your best to draw a sinusoidal curve lah. Okay, of course the peak will not change. Okay, so since this one is V input and this is against time, so this will be V output, V against time. I just put the standard unit lah, seconds. All right, so This will be the positive cycle, then this will be the negative cycle, and so on and so forth. So this maximum value here, V0, will translate here as V0 as well. Okay, so maximum is maximum, or they will all be V0. But you see, I'm a bit satisfied with this gap here. You see this drop? No good, no good. Although you could say, well, you know, 50 hertz times 2, that means the hums is 100 hums in 1 second. Barely can detect. But if we can have a more efficient current flow, why not? Okay, so in order to do that, we will do this process called smoothing again. All right, so we are going to install a capacitor in parallel to the resistor. So we'll place a capacitor here. Okay, I just draw it in black because no more colors now. And black is easy to see. So this is a capacitor C. We will place the capacitor obviously at the same position for both circuit lah. Alright, so this one is also a capacitor C. Okay, so I'm going to make a note here for people. I will say that the capacitor C smoothens the rectified alternating current. So what is the rectified alternating current? The second graph. This one rectified already ma. So how does it smooth? Well, my friends, like this. Whenever there is current flow now, let's say we talk about this yellow cycle. You see this branch here because this part is connected. So the current be like, hey guys, you see, we can also come here. Yes, and we can charge the capacitor. Okay, so meaning when current is flowing, the capacitor will charge. So I'm going to explain by a bit of drawing here. Okay, so let's just look at the capacitor and the resistor. The problem with the current through the resistor is that it is not constant. Current through this resistor is not constant. Okay, don't forget the current come from here. Okay, there's a complete circuit that I didn't draw. So current will enter here and then it splits. I mean, it is allowed to split into two this way. Okay, so when the current is flowing like this, let's say you're talking about this side of the cycle here, the capacitor will charge. Okay, so let us look at the graph and figure out where does charging happen. Charging will happen here when the potential is increased. So let's say the potential increase from here to here. Bloop. This side here until here is what we call capacitor charging. Capacitor charging. And don't forget the whole idea of charging, if you remember your chapter 18, means it is storing energy for a rainy day. Miss, when is the rainy day? The rainy day is when your voltage drop. So right now, this one will store up to peak voltage V0. This one is also V0. Everyone is happy. Unfortunately, this blue current is not going to stay there forever. Okay, so after a brief moment in time, what will happen to this is your resistor's potential difference will drop. Okay, so as mentioned just now, let me relabel it a bit. Here to here is V0. Okay, but after a while, the resistor is unable to maintain V0 because the AC current will decrease because it's about to change cycle. Okay, so you can see it will charge to V0 and then after that it will go down. So I would like it to go down slower. I have less ripple, go down slower. So what I'll do is the capacitor will now store energy. Okay, so the capacitor with the stored energy be like, hey, you were storing for a rainy day, right? Look at all this charge. Okay, look at all this charge. We were storing for a rainy day. Okay, so what will happen is the capacitor will now give back the charge or the current to the resistor, right? Because remember, this is V naught, and this one here is less than V naught. So the capacitor be like, hey resistor, what happened to you? Why your current drop one? Nah, take my one. So the resistor, although will still drop because the capacitor will not be able to maintain V naught, the current will flow back. So once the current through the resistor drop below V naught, what will happen is that this capacitor here, this one, the capacitor will decrease the charging effect like this. Okay, and then it will happen all over again. So I'm going to highlight this part yellow. Okay, from here to here, this part here, this is when the capacitor discharge. So when the capacitor discharge, it will return the energy. So from here to here, capacitor discharge, it will return the energy to the resistor. So this part won't drop as fast. And you have to make sure whenever you sketch this, whatever this potential is, it maintains the same one lah, because it's the same capacitor ma. So this one will drop this way, this one will drop this way. Okay, and I guess if you want to continue, it will still drop lah, this way. All right, so you will have charge, discharge. Okay, and then if you're wondering now where is the charging cycle, the charging cycle will be here. Boop, 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 boop. So here is charge. Where is discharge? Discharge will be here. Here to here, discharge. Okay, and depending on your drawing lah, something is wrong with my blue graph, but normally the charging cycle is smaller than the discharging cycle. Let me redraw this a bit. Okay, so this is the discharge cycle, and here to here would be the charging cycle. So I hope you get the idea. The capacitor will charge, discharge, charge, discharge, charge, discharge, charge, discharge rapidly, so that the current is always the same, or rather it doesn't change that much. So you go from, it doesn't go from maximum to zero. It goes from maximum to less, to maximum to less, but never drops to zero. Okay? All right, a few more technical things about the discharging curve. Although it may not be very obvious, this curve, very importantly, just going to put an exclamation point here, must be decreasing gradient. Why decreasing gradient leh? You can go and watch the capacitor video, because the discharging of the capacitor will follow the shape of a decreasing gradient, so something like this. Okay, so this one should look something this, decreasing gradient, that's better. So something like this. Just give me a sec to fix this. Okay, something like this, decreasing gradient. All right, we'll draw a few more in the examples lah. With the graph grids, it will be easier to see. All right, so something like this lah. Okay, so this is your full wave rectification for you. You have to rectify AC, and then that AC can also be smoothened, so that in the end of the day, right, you get a very nice pattern. All right, so let me label everything. This is the rectified AC. Such a thick line. Rectified AC is this one. Okay, with this charge discharge cycle, where you get this pink color shape, where you charge and discharge and charge and discharge. Okay, this one is the smoothened and rectified AC. Rectified now. Okay, and sometimes they will say something like, oh, size of the ripple. Okay, so let me draw the final form for you. Our Pokemon has evolved from this one to the humps when we connect to the diode, to this ripple wave-like shape when we connect to the capacitor here. Okay, so at this cycle, Here, let me label for you the capacitor charges. So here we can say that the C charges. And here your C discharges or loses energy and feeds it to the resistor. Alright, so I will show you how the final form looks like. Okay, so the final form will look like this lah. This is the trace that you will see on your CRO. I'll show you the simulation later, but this explains a lot of this. Okay, so I know it's also not very obvious in the sketch. I got this from a past year question, that this part here is still decreasing gradient and this part is the starting point of a sinusoidal wave. Alright, and the change in voltage, the variation in voltage, which is called smoothing, is smaller. Alright, so what's the advantages of full wave rectification? You get a larger mean current because now you have the beauty of the whole wave and it's more efficient lah, basically. So I will just put a note here. The advantage of full wave rectification, you have a larger mean power output. That will be the obvious one. Okay, then you can say because you are using the whole wave, not half of it, and then when you add capacitor, you create an even larger mean power output because the capacitor helps the circuit store energy. All right, so now before I move on to the simulation, what did we learn today? We learned that drawing this can be pretty straightforward if across the parallel sides we align them in the same direction, and this thing can be rotated. Should you get stuck because somehow you did put them parallel pointing the same direction, like in this example, however, you reach one point, the current cannot enter both diode. That means you're wrong. Or the current can enter both diode and you don't know which one to go. So immediately upon entry here, it should be very obvious where the current will go. The current will go to the blue one. Let's say for this one, you go to the bottom side, it should be very obvious where would the current should go, the green one. If it's not obvious, means you're wrong now. Okay? So once you connect this, if let's say you are wrong, what you need to do is you need to flip one and flip the opposing one. Alright, that's just a technique lah. Or I guess you could memorize the circuit. Okay, so do some examples. There will be different variations of this circuit. As long as you can chart the direction of current flow and if needed, draw an arrangement of arrangement of diodes like this with the correct symbol. Alright, so when we arrange the diode in such a way, the output through this resistor will always flow in the same direction. Meaning now we have a modulus alternating current graph. The negative will flip up to the positive, flip up to the positive. So then when we add the capacitor will smoothen. Then you get this ripple. And the advantage of this is you have a larger mean output compared to half wave. We are not wasting the half wave.